Recently, there was a paper published with the title, "Are Most People Too Dumb for Physics?" Why that? Because some professors, not our colleagues, they believe there is no point to teach physics at all. Why? Because physics is too difficult for an average mind. Then the physics has no relevance. Then later students would graduate, they would go to engineering or history, they wouldn't need physics. And then conceptual physics is way too shallow. And three professors, including Eric Mazur from Harvard, they care about teaching. They wrote a paper, they disagreed completely with the statement. And from that paper, I want to bring one quote. From their point of view, one of the basic learning outcomes of a physics course is the ability to solve problems. Yeah, this is the most students would learn from our physics classes, and I believe from math classes and other classes. Because they may forget something specific, but how to solve problems, how to think, they would take with them forever. And then imagine if you are visiting a doctor, and that doctor, well, maybe remembering something specific, but isn't a good problem solver. Then you would feel you can be in trouble. The same for teachers everywhere. So we want people we communicate to be good problem solvers. And then we want our students to be good solver of problems. It's our responsibility. And I was lucky bumping into that book written by Nobel Prize winner, as I mentioned to you, Daniel Kahneman. And it's written for psychology majors, for people in business, but reading that, I saw explanations to what I saw in my classes. And then I asked myself, would it be possible to apply anything from over there to improve problem solving in our classes? And the idea is following, that we have like two systems in our brain, in our mind. The first one, it's mostly autopilot. This is the way we navigate. We drive empty road. We don't think about driving. We're on autopilot. And we do many things on autopilot, because that system is very good to generate quick solutions, not for real problems. Looking for a pattern, yeah, this is what I did, it's going to work. But then when we have a problem, what happens? For us, professors, when we teach some subject for years, and if there is a problem, we go through the left line, what is called expert solution. Spontaneously, immediately, we see an expert solution. We know how to solve that problem, even without thinking about that. Why? There is no mystery behind expert solution. It's just a result of practicing. And people, again, playing music, they know you want to be a master, you are supposed to practice a lot. And we practice it so much, we just do that automatically. But our students, they're on the right side. They are not experts yet. So, and then they are trying to do what is called intuitive heuristics. And they have very many biases. And many biases are common for very many people. And if we understand biases for our students, then we may address the problem better. And then the second type of thinking, what is called slow thinking, or system 2 in psychology, it's slow, it takes a lot of mental energy and effort, but actually this is where we solve problems. When our first system isn't able to generate solutions, then normally we go to the second system. And that system, yes, we may control our thoughts, and that system is very powerful, but then it takes a lot of energy. The problem in physics classes, and I believe probably in other classes, the students going through the right side, this intuitive heuristic, they pick up some solution, and that solution is wrong, could be wrong. And I learned recently that to know that you are wrong, you are supposed to be good enough to know that you are wrong. But they are not good yet. And they stop there, they don't go into this slow thinking mode. So we need to find a way to help them with their intuitive thinking and push them to use their system 2 or slow thinking. A couple comments again, from the book, about intuitive heuristic, that when we are faced with difficult questions, especially under time pressure, what happens, quite often we substitute the original question on easier question. And then I thought, well, now I understand, because in many cases I saw the students doing midterms or final exams solved some different problems, not problems I gave to them. And I thought, well, probably they wanted to pick up some extra points. No, it happens. They just don't see they're solving a different problem. And in the book of Kahneman, there's an example. Let's say there's a stockbroker who needs to solve a problem, whether to invest into, let's say, Ford Motor Company. And it could be a difficult question to evaluate the market, and under time pressure, a boss is coming and you need to produce answer within 5 minutes, that somebody may substitute the original difficult question into an easier one. Do I like Ford cars? Oh yeah, I like. Okay, let's invest. This is what students do. So we need to find a way to prevent them from this jump. The other example, availability heuristics, and what people remember, what is easier to retrieve from memory, then they believe it has more value. And it also explained to me what I saw in my classes. I saw that some students were trying to solve all problems on, let's say, some midterm using just one equation. Because it was just one equation, they remember it. And that was only one available to them. So we need to find a way there's more in their memory. Yes, and a problem, yes, students try to consider any problem isolated from anything else. And I'm not joking, you give them a problem, let's say, about a cat jumping from a roof, and then 2 days later it could be another problem, and another problem it could be, let's say, an elephant. And for students, some students, there are going to be two different problems. Like a cat problem, like you need cat equations in physics, and then an elephant problem, like you need elephant equations in physics. They don't see it's the same. For us, it's obvious. For them, it's not so obvious. About slow thinking, yes, system 2 is the only one that actually solves problems. But at the same time, that system needs concentration and attention. And our attention budget is limited. So when we do something else, it means we have less attention for system 2. And this is what happens with students. They think about Facebook, and it means less attention for actually solving the problem. And then the other, intensive focusing on one task, can make people effectively blind. We can be blind to the obvious, and we're also blind to our blindness. It's not so much for students, I believe it's for us. When we're so much involved into something, we may not see something else. And it's normal, you know, there is nothing wrong with us. That's the way our memory operates, our brain operates. The other, reading a book written by a psychology professor from Scotland, I believe, I bumped into an idea that thinking and writing, there are two different activities for our brain. And then I thought, wow, what we do at ODU, placing so much attention on writing, is actually great. Because when we think, we normally think spontaneously. We jump from one place to another. But when we write, we need to create a story. We need to think logically. It means we engage our system too. That's what we need to do in our science classes. We want students to engage the system too, and through writing. So writing not only in history classes or literature, well, in science classes too. About 2 years ago, there was an experiment in my class. It was in physics 231, and later I started using that in other 231 classes, also 111. 231 is introductory physics calculus based, 111 algebra based, and communicating with my colleagues, so we implement more and more of this approach. So what is the idea? I don't have much time to go through every point saying how to connect that point to ideas in the book published by Daniel Kahneman. So I'm going just to tell you what do we do. So we enforce students to follow these 6 steps. They are general steps. They are not specific for some specific chapter. They are general steps. It's kind of a refinement, ideas from Paula, but keeping in mind of psychology, how do we solve problems. And number 1 is following, name and write down, write it down, the type of physics most likely related to the problem. So we want students to write down, to engage their system 2, slow thinking, what is there. And after that, the next step, write down most basic equations for this chapter or for this physics. On if student believes there is more than one physics, okay, write down more. What happens in this case? In this case, instead of trying to guess a solution, it's like being a police detective. You place all your suspects in one room. And then your problem is easier. You know, somebody who did it sitting in this very room. It's much easier than going around trying to guess where it could be. Then the next step, simplify these basic equations as much as possible and do it in symbols. Because very many problems, they're easier than basic equations. And when students do that, they see a way to actually solve them. After that, when they have this, we may say, adjusted equations, solve them again using algebra, using calculus, no numbers. Because I believe when somebody sees numbers, then physics is lost. So you need to think with symbols, like happens in nature. And then when you have a solution in symbols, plug in numbers, and the last very important step, maybe the most important, evaluate your answer using common sense. Yes, in physics it's possible to do that. Use your common sense. And let's see what students say, and I pick up some, again, their comments after the class. And practically in every comment you may find that word thinking. And I thought, wow, that's good. So we teach not only physics, we teach them how to think. And again, even more on the other page. And at the end, at the same time, I just want to tell you that in some cases, the easiest way to solve problems is this one. Yeah, thank you.